Welcome to our explainer on Mastering the Cambridge AS Level Physics Paper 3. I am the strategist and I am absolutely thrilled to guide you through this today because we are going to do something crucial. We're going to decode exactly what examiners are looking for to secure your top grade. Look, if you have ever walked out of the lab feeling like you did the experiment perfectly, but then you somehow still hemorrhaged marks on the write-up, you are in the exactly right place. Today, we are going to look at the precise blueprint of the practical examination. We're pulling directly from the Cambridge Study and Revision Guides to show you how to frame your answers and highlight the key evidence the marking scheme demands. No more guesswork, no more leaving marks on the table. Okay, let's dive right into this.
Here is our roadmap for this explainer. We're going to cover the complete practical exam blueprint. We'll look at how to handle variables in data collection, how to present absolutely flawless data tables, and the strict rules for drawing the perfect physics graph. Then we'll get into the math puzzle of extracting constants, and finally, how to critically evaluate uncertainties and limitations. We are breaking down the entire experimental process, from your very first measurement to your final critical evaluation.
So, Section 1, the practical exam blueprint. Let's talk about what is actually at stake when you walk into that laboratory. 40 marks. That is what's up for grabs here. 40 marks, making up almost 1/4 of your entire AS level examination grade. These 40 marks are divided equally between 2 questions, meaning every single point you earn or lose carries massive weight. Think about that for a second. 1/4 of your grade rests on your ability to not just understand complex physics theory from a textbook, but to actually do physics in the real world under high-pressure, timed conditions. You have to prove you can think on your feet. The paper assesses 3 core skill areas equally. First up, manipulation, measurement, and observation. This is basically your physical competence in the lab. It's your ability to handle common laboratory apparatus, your micrometers, your voltmeters, your stands and clamps, and precisely follow instructions to set up the equipment. Second is the presentation of data and observations. This is all about your tables and your graphs. Can you organize reality into clean, structured data? And third, analysis, conclusions, and evaluation. This is where the real critical thinking comes in. You'll calculate uncertainties, extract hidden constants, and boldly identify the physical limitations of your own experiment.
Moving on to Section 2, variables and data collection. This is where we set up for success before we even touch a piece of graph paper.
Before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, back to variables. You absolutely must know the difference between these two, because getting them mixed up will cascade into massive errors in your tables and graphs. The independent variable is your input. It is the variable that you physically control or change in the experiment. The dependent variable is the output. It's the variable that changes as a result of you messing with the independent variable. It's cause and effect, plain and simple.
Let's look at some real examples. Take a bouncing ball investigation. The height you initially dropped the ball from, that's independent. You chose that. You controlled it. The height to which it bounces back up, that is dependent on where you dropped it from. Or take melting ice and water. The initial temperature of the water is what you set. That's independent. The time it takes for that ice cube to fully melt is the result. That's your dependent variable.
Now, listen closely to this strategy. When you plan your experiment, you cannot just take a couple of quick readings and call it a day. To get valid results, examiners want to see a minimum of 6 sets of readings. And here is the absolutely crucial part that trips students up. They must be evenly distributed across the widest range your equipment allows. If you clump all your readings together, you won't see the trend. For example, if you were doing that melting ice experiment and your water can be anywhere from 100 degrees Celsius down to 10 degrees, a sensible wide spread would be taking measurements at roughly 95, 80, 60, 45, 30, and 15 degrees. Stretch it out.
Let's head into Section 3, presenting flawless data tables. In Paper 3, precision is everything. These 3 steps are your golden rules for tables. First, draw your table before you start collecting results. Don't scribble data on the back of your hand. Have the structure ready so you aren't scrambling. Second, your raw data precision must be consistent, and it must exactly match your measuring instrument. Never try to fake precision. Your raw data decimal places must reflect what your actual ruler or stopwatch is physically capable of showing. Third, when you calculate new data from those raw measurements, like squaring a time or dividing a voltage, the calculated quantity should be given to the same number of significant figures as, or one more than, the raw measurement with the least precision.
Let's actually apply those rules to a flawless table. Notice the column headings. Every single one includes the physical quantity and the unit, separated by a forward slash. Look at the potential difference, the PD, in volts. Every single reading is recorded to exactly 2 decimal places. Now, look really closely at the asterisk on 0.350 in the average current column. The 0 is retained. Why? To prove to the examiner that the current was calculated and measured to the nearest milliamp. If you just wrote 0.35, the examiner's red pen is going to come down hard and you would lose a mark for inconsistent precision.
Moving right along to Section 4, the perfect physics graph. This is where we visualize your hard-earned data. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions.
Okay, let's talk about the 5 golden rules for graphs. 1. Label your axes with the quantity in unit, putting your independent variable on the x-axis. 2. Choose sensible scales so your plotted points occupy at least half the sheet of graph paper. Avoid awkward scales like 1 to 3 or 1 to 7. They make plotting an absolute nightmare under time pressure and invite silly mistakes. 3. Plot accurately. 4. Draw a proper best fit straight line or smooth curve. And remember, you do not have to force your graph through the origin if the physics doesn't dictate it. Think about a mass hanging on a spring. The intrinsic mass of the spring itself means the dependent variable won't be 0 even when your added mass is 0. Finally, Rule 5, clearly identify any anomalous points that don't fit the trend.
I need you to burn this into your memory. Examiners hate blobs. You must plot your points using a small, sharp, saltire cross, an X drawn with a very sharp pencil. Why? Because tiny dots are difficult to see and they disappear under your line of best fit. Heavy blobs are imprecise and obscure the exact coordinate. In a physics practical, any lack of precision will be heavily penalized. Draw sharp crosses.
Now let's look at what happens when you draw your line or curve of best fit. When drawing a curve, it must be a single, confident sweep. Look at graph A on the left side of your screen. That is a beautifully drawn, smooth curve. Now look at graph B on the right. If you sketch it with nervous, jerky, feathery strokes, or if you kind of awkwardly connect the dots between your points, you will lose marks immediately. You need to practice making that single, continuous sweep of the pencil. It shows confidence and mathematical understanding.
Section 5. Extracting constants from graphs. This is the math puzzle, the climax of the experiment where you pull hidden truths out of your data. You all know the basic formula. Gradient equals the change in y divided by the change in x. But the practical application in the lab is where students constantly trip up. To find the gradient, you must pick 2 coordinate points directly on your drawn line of best fit. Do not just blindly reuse data points from your table unless they happen to lie perfectly dead center on the line. And crucially, to improve precision, these 2 points must be as far apart as possible. At the absolute minimum, the distance between them must be at least half the length of your entire drawn line. This minimizes your percentage error. Finding the y-intercept can also be a massive trap. The y-intercept is the point at which the line cuts the y-axis, meaning where x strictly equals 0. Beware of false origins. If your x-axis doesn't start at 0, which happens a lot so you can stretch your points across the page, you can't just visually look at where the line hits the vertical axis. That's a trap. You have to calculate it mathematically. You take the gradient you just painstakingly found, pick one of the coordinates exactly on your line, and substitute them all into the equation y equals mx plus c to solve for c.
Finally, Section 6, Uncertainties and Limitations. This is where you prove your critical thinking skills to the examiner.
Let me be blunt. Stating human error is a forbidden phrase. Stating parallax errors with no context isn't enough either. You will get 0 marks for that. You must specify exactly where the error occurred in the physical process. For example, if you're working with a swinging pendulum, you can't just write parallax error. You need to state parallax errors when judging the exact highest point the pendulum bob reaches. You have to tie the limitation directly to the physical action you performed.
Let's break down how to actually estimate these uncertainties. For analog instruments, like a meter rule, the absolute uncertainty is usually the smallest scale division, like plus or minus 1 millimeter. But what if you take repeat readings? Say you time a pendulum 3 times and get 10.17 seconds, 10.04 seconds, and 9.93 seconds. The easiest trick in the book is to calculate the range, which is the highest minus the lowest. 10.17 minus 9.93, giving 0.24, and simply divide by 2. So your absolute uncertainty is plus or minus 0.12 seconds. Easy. And remember the golden rule of thumb. To support a hypothesis without doing insanely complex calculations, your calculated experimental values should generally lie within 10% of the theoretical predicted values.
Let's practice identifying weaknesses using that melting ice experiment as an example. A true critical thinker immediately realizes that room temperature air is going to mess with the ice's melting time. What are some other weaknesses? Well, taking only 2 readings is never enough for a mathematically firm conclusion. The ice cubes you pull from the bucket might not have the exact same starting mass. There are unwanted thermal energy exchanges with the surrounding environment, and honestly, the ice might partly melt in your warm hands or on the desk before it even hits the water beaker.
Once you find the weaknesses, you have to provide highly specific, actionable cures. Identifying the weakness is only half the battle. So how do we fix the melting ice experiment? Instead of just vaguely saying, take more readings, you write, take more sets of readings at different water temperatures and plot a calibration graph. To fix the mass issue, weigh the ice cubes on a top pan balance first. To stop that unwanted thermal energy exchange with the room, carry out the experiment inside a vacuum flask. And to prevent premature melting, keep the ice securely in a cold refrigerator until the exact moment it's required. Precision is a mindset.
The art of physics is critical thinking. It's about acknowledging that our laboratory tools and our human methods are imperfect, and constantly asking yourself how you can push the boundaries of precision. Think about the bouncing ball experiment. It is incredibly hard to accurately read a peak bouncing height by eye in real time. So a brilliant improvement you could suggest is to film the experiment against a fixed scale and play it back in slow motion. Next time you run an experiment, ask yourself, are you just relying on your own eyes, or are you truly pushing for absolute precision? Students who implement these physics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGSC to excel in your Cambridge examinations. Subscribe right now to acetheexams_IGSC and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here.